Hello everyone, welcome back to alkaline hydroxide 784, and today we will be doing something in the chemistry series which is related to titration curves. Yeah, so it is like a follow-up to the last episode that we just did. And yes, this is the first time I'm recording the audio after the video, so I hope it goes well. Yeah. Okay, yeah, let's move on. I have to wait for the video to show stuff. Okay, so the first thing we'll be doing is looking at the just a titration curve as you would expect from a monoacidic, you know, acid and base reaction, and a strong one in that sense. So what a titration curve shows is the change in pH, and usually you would be adding either the acid to the base or you'd be adding the base to the acid. I think in this scenario, in all of the scenarios today, we'll be looking at adding NaOH to all of the acids that we're going to show today. So yeah, the reason why it's called the titration curve is because you'll be doing it during titration, so you can actually add a certain amount of NaOH when you're doing the titration. Using your burette, you can measure that. Okay, so yeah, so finally I have come to the strong acid, strong base reaction. We're gonna look at monoprotic slash acidic ones because it's just easier that way. I mean, that's the most basic one. So yeah, I do not know why I bothered to draw the graph with the set square because I didn't actually do it after that. How exciting. Okay. So yeah, as you can see, it's just like one like a small increase, then the sudden increase, and then another small increase. But is where the big change, like the rapid change in pH occurs. And yeah, so as I said, all of the acids and bases here will have the same concentration. I don't know, maybe 0.1 mole or something, mole per dm cube. And we're gonna use as a basis 25 milliliters of each of the acids inside the beaker or the flask or whatever you put your acid in. Of course, in reality, you wouldn't be putting 25 milliliters of HCl in your beaker because your burette may not really, like, you don't want it to have more than 25 milliliters of NaOH dispensed at any one go. But anyways, let's just go with that. As you can see, the part where the rapid increase occurs is when the HCl and NaOH technically react completely with each other, and therefore we can call that the equivalence point, and that will be when 25 ml of NaOH is added because we are saying that they are the same concentration. So you're just gonna go in the same volume because the concentration is the same. So yeah, it be like they both reacted with each other completely. There is neither acidic nor basic at this point. I do not know why I did write that a little bit too quickly, but technically that's like the half equivalence point around 12.5 milliliters of NaOH, but we'll look at that later. Okay, so the next one is yeah, sorry, I have to adjust the papers. Okay, so the next one is with a is it a diprotic or biprotic? I don't know. Like basically an acid with two hydrogens to lose. Of course, now we will be looking at a weak acid, so it's not really as strong as HCl, but it's not really that bad. It's actually okay. We're gonna look at bicarbonate. So H2CO3. Wait, sorry, is it bicarbonate? Okay, I don't know. This is carbonic acid, I guess. Carbonic acid. And you will get carbonate anion there, and you have two H plus in that sense. So if you're gonna use NaOH, the first thing that happens is you react it with one NaOH and you will get the bicarbonate anion with Na, so you get sodium bicarbonate and H2O. So of course in reality the sodium and bicarbonate will still be dissociated as ions, so you can still react with the bicarbonate ion. So instead of if you were to just put it as sodium bicarbonate with another uh, sodium hydroxide, you would then get disodium carbonate, so Na2CO3. Yeah, I don't know why I cancelled that. I guess I was confused as to what exactly I wanted to show. But of course, if you wrote it in terms of an ion, you would be getting like HCO3 minus becoming CO3 2 minus. So that's the idea behind this. Okay, great. So that's the two equations that we see for carbonic acid, is it? I don't know. Yeah, I think it's carbonic acid. And then I decided to write stuff and then I didn't know that it was being hidden. Okay, actually I think I will probably shift it up again, right? Will I? Don't know what I wrote there, honestly. Anyway, here's the titration curve. So I'm gonna draw the titration curve for the carbonic acid. So once again, we'll be looking at 25 milliliters of carbonic acid and oh yeah, I just realized this one was not very legitly proportional because I drew the first part too much. Okay, sorry. But okay, so the point is we'll be having like 25 milliliters of carbonic acid in the beaker, and we'll be adding NaOH to the beaker, and they both have the same concentration, maybe 0.1 mole per dm cube or something like that. Yeah, I apologize for my terrible drawing. So this time I'm gonna properly proportion the graph, and yeah, so the first rapid increase occurs at 25 milliliters, and the second one will occur at 50 milliliters because there's only two of them. So yeah, and apart from that, it's pretty unrapid increase in the sense. So the first one will be like the first equivalence point, and it's about 8.3 pH, like the pH of 8.3. And the second one at around 50 milliliters is around pH of 10.3. So it's actually quite high. Both of them are above 7, which means that methyl orange technically doesn't work for this. So what does work for this? We will look at that later on. So the first equivalence and second equivalence is there. And then finally we can go to the concept of equivalence point. So the half equivalence point is when for example, if you're looking at the first one here, it would be the concentration of the carbonic acid equals to the concentration of bicarbonate. Yeah, and the second half equivalence point is when the concentration of the bicarbonate is equals to the concentration of the carbonate anion. Yeah. So as you can see me writing it down there. So that's the idea of the equivalence point. And I guess since we are using equal concentrations and stuff like that, it's pretty obvious to see that the first one is occurring at around 12.5 milliliters of NaOH, and the second one would be around 37.5 milliliters of NaOH. Yeah, so not very exciting, huh? Okay, so yeah, I can see my newspaper underneath. So basically, how do we calculate the these half equivalence points and stuff like that? An equivalence point. I guess the half equivalence point can be just done by, like, you can look at the volume part, you just divide by 2, we get the half equivalence point. But the easier way to look at it, if you're looking at the pH part of it, the pH at the half equivalence point is equals to the pKa. So if you're looking at a buffer solution, for example, it will be actually around that point. That's why the area changes pH very, very slowly or like very minimally. Then no longer quite a large concentration of both the acid and the conjugate base, as you can see. like the carbonic acid and bicarbonate ion, which is actually a conjugate base. And therefore you can actually use this as the buffer. So when you're calculating a buffer pH, you can take your pKa1, and then yeah, you use the equation plus log of bicarbonate or carbonic acid. Yeah. Okay, so yeah, I just explaining how what pKa1 refers to and pKa2 refers to. I hope you actually know what they refer to. Okay. Uh, as for the actual equivalence point, there's a bit of an issue with trying to calculate it here, so I will try to explain that later. But as of now, I'm just gonna say, maybe use the pKa value, but there is a problem which we can look at later. Okay, I'm just taking forever. But yeah, technically the thing that you would think of doing is to look at the equilibrium, right? Because we have the K equals to the concentration of the products over the concentration of the reactants. But okay, so next we move on to the most important thing here, which is the triprotic acid, phosphoric acid. And yes, it's actually quite an important anion, the phosphate anion, the PO4 3 minus anion is actually quite important in biology. But okay, that's not very important. The important thing is to look at the titration of phosphoric acid. So as it is a triprotic acid, the first one will be like H3PO4 becoming H2PO4 minus. Then if you added one, like 25 milliliters of NaOH, then if you add another 25 milliliters, you will get from H2PO4 minus to HPO4 2 minus. If you add yet another 25 milliliters of NaOH, you will get from HPO4 minus to HPO4 minus becomes PO4 3 minus 2. Wait, what? No. Actually, I just confused myself. I don't remember what I just said. Okay, so the first one is H3 to H2, then H2 to H, and then H2. No H. Yeah. I hope you understood what I mean. You can just write it down yourself because I kind of forgot to write it down. But I actually got the data for this from somewhere, so I'll write down all of the data here, which is like the starting point, all the equivalence points, and the half equivalence point. I'll share the link below, don't worry. Because obviously my drawing is not paying due justice to the original thing, which looks way neater and a lot more accurate. But yeah, the numbers are correct as far as I can tell. Yeah, as you can see, the first half equivalence point is at 2.12, and the equivalence point is 4.67, which means you can use metal orange, I guess. And then the second equivalence point is at 7.21, and then half equivalence is 7.21, equivalence is at 9.46, then third half equivalence is 11.66, and the last one is the actual equivalence point 11.93. As you can see, the last one is not very rapid change, because by the time it's actually quite very weakly acidic. It's more basic than acidic at this point. Yeah, so I wrote down all the species at each equivalence point, so maybe you can write your equations with that information. So as you can see, like every 25 milliliters of NaOH, you get one so-called rapid change, the equivalence point. Of course, you're assuming that the concentrations are the same. Actually, not assuming. I'm saying that they're gonna be the same concentration. Like that's my context that we are working with here. Okay. So as I mentioned earlier, the half equivalence points are equal to pKa. So pKa1 is 2.12, pKa2 is 7.21, and pKa3 is 11.66. And it's very easy to calculate the Ka for all of them, which would be 10 to the power of negative pKa. So Ka1 is 10 to the power of negative 2.12, Ka2 is 10 to the power of negative 7.21, Ka3 is 10 to the power of negative 11.66. So, yeah, from there you can try to attempt getting the pH. The thing is, I never really told you what's the concentration of this whole solution, right? So, right, I mean, I'm just gonna assume the initial concentration is 0.1. But the problem with this whole thing is that the problem with doing this is that you probably won't get the answer because of one big thing. So yeah, let's just watch myself attempt to do it. So I guess you can easily get the half equivalence point pH, and then I start to write stuff before I even move the paper. Yeah, so at the first equivalence point, you can tell that all of the H3PO4 has become H2PO4 minus, right? But the thing is that doesn't mean that it is permanently H2PO4 minus. Of course, it is very likely that's going to be there, but it is possible for the H2PO4 to become H3PO4 again. Yeah, so but it should major, and at the same time it's not very likely for it to become HPO4 minus as well, so I'm not sure of how either of the things will work. And yeah, and actually I just realized that the concentration would have changed by now just because you added a bunch of NaOH to it, and the volume of water is bigger now. There's actually a lot of things to consider. Oops, okay. Seems like, trying to use that usual method that we use with the S squared over the thing, it doesn't give you the answer that you wanted, because since Ka1 is like what 10 to the power of negative 2.12, and if let's just do a whole assuming S doesn't really do much, because actually I think at that point it doesn't really dissociate much. So S is gonna be pretty small, and then we put 0.1 maybe. And then if you times 10 to the power of negative 2.12 by 0.1, you get 10 to the power of negative 3.12, and then you can probably square root that and you won't get the answer that you wanted, because it's nowhere near that answer. Yes, like this is the point of time where I basically realized that I didn't know what was going on. I was like trying to calculate stuff in the calculator and it didn't work, unfortunately. I guess we have to actually consider the KB as well and not just the KA part of it. So it's not gonna be very accurate. Yeah, I'm taking way too long to move move from here. Oh no. Okay, yeah, but that's why you should be a bit wary about calculating the pH at this without any data. So make sure you have some kind of data before you do any calculations. Don't just come up with data on the spot, because technically I could put literally any number there and it still wouldn't make a lot of sense. Yeah, as I have written down here, I guess it doesn't really work. Okay, let's move on. Okay, so the final thing I suppose is actually talking about the indicators. So as we remember in the last episode, the indicators are based on which pH range you want to look at. So yeah, as we know, like if you're using a strong acid, weak base, you can use methyl orange. If you're using a strong base, weak acid, you use phenolphthalein. Wait, what? Yeah, I finally write about, oh, you're gonna look at indicators, yay. Yeah, but yeah, you know what I mean. So if you're looking at the carboxylic acid one, we know that 8.3 is a little bit too high for methyl orange, but it is in the right range for thymol blue. And 10.3 can be used for phenolphthalein. So what we will do is add one of them first, and then we do the titration until that point, like until 25 milliliters, and then you see the change in color. And then afterwards you add the next one and you continue the titration to find out the next point. Of course, in an actual practical experiment, you may not know the concentration of one of the reagents, and the point of using the indicator is to figure that out. Yeah, that's the reason why you need both of the indicators, and they will not be the same thing. So you need to know the color changes for whatever indicator that you're using. So for the phosphoric acid, you could technically use methyl orange for the first one, and then the second one you can use phenolphthalein, and the third one is just, I don't know what to say about that. The third one looks pretty hard to actually find out, so yeah. But anyway, I don't think you really need the third one. Do you? Okay. Yeah, you can just calculate it using the first and second one. Anyway, yeah, we are kind of done here, I think. But the thing is, actually, the third one, maybe you could use this other indicator, but you don't need to know this, so who cares? If you really want to know what this indicator, like how I found what indicator this is, it's in the same link that I mentioned earlier. Just go and click the pH range one. So basically the link has a bunch of images, and you can click different titration curve images or image on the pH ranges of these indicators. Yeah, so we're done, I think. Yeah, if you have any questions or comments, do it in the comments below. If you found this video useful, please press the like button and subscribe. Thank you, bye!